Ee, Herkese merhabalar. Ben Muzaffer Sevili, ITP Computer Society Türkiye gönüllüsüyüm. Bugün CS Talk serimizin 13. bölümünde e, Brown University'de Postdoctoral Researcher olarak görev almakta olan Sayın Alper Ahmetoğlu, Deep Symbol Generation and Rule Learning adlı sunumunu yapmak üzere bizle birlikte olacak. Teklifimizi kabul ettiğiniz için hocam öncelikle teşekkür ederiz.
Ben
Öncelikle
teşekkür
sunuma
ederim.
geçmeden nasılsınız diye sormuş olayım size.
İyiyim, teşekkürler. Geliz Genç için teşekkür ederim. Sen nasılsın Muzaffer?
Ben de iyiyim hocam. Teşekkür ederim. Tekrardan davetimizi kırmayıp kabul ettiğiniz için teşekkür ederiz. Dilediğiniz zaman sunuma geçebiliriz.
Tabii ki ben de teşekkür ederim. Beni burada konuk olarak görmek istediğiniz için, bana bu imkanı tanıdığınız için teşekkürler tekrardan. E, Bugün sunumu İngilizce yapmayı planlıyorum. Biraz daha belki ulaşılabilirlik seviyesi artması açısından. Ama sorularınızı İngilizce, Türkçe sorabilirsiniz. O zaman daha fazla uzatmadan başlıyorum. Tekrar herkese merhaba. Herkese geldiği için teşekkür ederim. Today I'll talk about my what I have done through my PhD and my PhD work, but I will first give some sort of motivation on why I am doing this and why I specifically did research on this topic, deep symbol generation and rule learning, and I'll talk about what these symbols mean and what rules mean and what do I mean by all of this. So before starting, let's talk about our ultimate goal, which is artificial general intelligence. I think it's quite safe to say that all of us working in the AI field, or at least most of us working in the AI field, is trying to achieve something like this, right? Like we have a general purpose robot that can do many tasks. For example, our household robot that can prepare our food, that can take the rubbish out, clean the room, do any kind of mundane tasks, and not only mundane tasks maybe, but like teach our children, talk with ourselves, accompany us, and so on. And this is the intelligent behavior that we are aiming for. And to reach this, there are like several requirements that we need to satisfy before achieving such ambitious goal. And it needs to be like the system that we will find needs to be safe. So we need to understand how it's working. For example, you wouldn't get on a plane if you don't understand the inner mechanics of it. Like if you don't have some faith in the sense that the plane would not crash or so on. There are very strict requirements for aero traveling. And for example, you wouldn't leave your kid with the robot if you don't trust its behavior, right? This robot needs to be general purpose, like it should be programmed fairly easily for different needs. For example, if you want the robot to clean the room, we should just say, okay, clean the room. Or if you want to do some other tasks, such as taking a walk for our dog, then we should be able to tell it so without uh, changing a lot of structure in it. And for example, you might consider ChatGPT as some sort of general purpose agent that lives in the textual modality and natural language modality. And in order to, so what sets this problem apart from the ChatGPT, like the AI we currently have, is that robots need to live in the real world as opposed to internet. And in order to operate in the real world, it should have some advanced sensory motor skills. So it should parse its environments, understand what objects are in it, what the current configuration of the environment through its multiple sensors, through its rich sensory input, such as multiple cameras, LiDAR sensors, force feedback on the joints, and so on. And it should also have a very good actuation functions, such as like be able to grasp objects fairly easily in order to do many different tasks. or actually, at least we should have some sort of a very good embodiment of the robot that can do many tasks without some limitation. And if we want to have these robots in daily lives, since not everyone can, if you want to have this robot talk with many people, then the most easy way to communicate is the natural language. For example, ChatGPT gives you the ability to talk with it without knowing its inner mechanics. So even if you do not know anything about AI, you can already talk with ChatGPT and let it do your tasks. So we need to be able to communicate this robot using natural language, or maybe some sort of gestures, mimics, and so on. And it should have a high level understanding of our goals. For example, if we say something, some goal, for example, clean the living room, it shouldn't just take all the objects in it and throw it out in the rubbish, because maybe the living room currently has my mobile phone in it too. And it should understand our goals, what do we mean by them, and should reason about them, how to reason about the steps to achieve them. And this has some connections with language and planning. So these are at least some set of requirements that we need to address in order to achieve this highly ambitious goal, right? And there may be more requirements than that, actually. But this gives you a picture of what we are aiming at, right? And the current paradigm since 2012, after the foundation of the AlexNet, where AlexNet is a type of deep neural network that won the ImageNet competition on 2012, and that showed the field of machine learning that we can use deep neural networks to learn abstractions, solve a task without introducing structure to solve a specific task. This was a big news because now for different kinds of tasks, we don't need to find the good abstraction model to solve that task, but just throw a very deep neural network that takes the whole raw data as input. In the AlexNet case, it was the image, pixelated image, and output the correct decision. And this trend actually went on, and with the addition of the transformer models, where you can now model very long sequences of text because of the transformer model. Now we can have models like ChatGPT and so on, where you can basically model anything in the text modality on the internet using ChatGPT and so on. So this idea is basically throw a very large deep model, throw a lot of data in it, and then you will get the answer. And because this trend succeeds currently, at least in some tasks, for example, for the machine translation domain, or for some simple translation domains, this works very good. Now people start to ask in the robotics field whether we should give up the rest of the robot research and collect 100 million diverse high-quality text demonstrations. This is a very notable researcher, and he's actually asking this question unironically. Should we give up a 1 year of robot research to collect 100 million diverse high-quality text demonstrations? So this is a serious question, because models like large language models, ChatGPT, and so on, showed us that indeed we can throw a lot of data to a very large model and get good results. And there are some works that shows scaling laws that shows like with increased amount of data and with increased amount of parameters, your results would get better. But so this is like one hypothesis, one general hypothesis of the solution to AI. But there are some evidence to it, like ChatGPT shows that if you train it on an internet scale data, you can get good results. But can we say this? Can we say this will be true in robotics as well? Like, can we say this will hold in the real world too, where we need to interact with the objects and the word configuration is vastly different than the text modality? And to connect with to connect that deep models with robots, would that be feasible with this kind of approach? Well, actually, we have seen autonomous vehicles, and they are kind of like taking this approach currently, at least some of them. And we have a lot of data for the autonomous driving problem, but we currently don't have, I don't want to say we don't have the solution, but we don't see the magic of deep learning in autonomous driving currently. And if you think autonomous driving, it's actually more structured, even though there are a lot of non-structure in it, like roads might be different, signs might be different, there may be some pedestrians, some pedestrians distribution might be different in different countries. Some countries have a lot of bikes, some don't. And even though there are a lot of variations in the world configuration, if you compare it to a real world where rooms might have different configurations, or like different cities have different configurations, consider San Francisco and Istanbul, those are vastly two different cities. And then you get a lot of, so then you can see that roads are actually more structured environments than the real world. And if this doesn't work on the roads, then we might get a little bit suspicious about whether it will succeed in the real world. And one other approach to connect the foundational models, like the advantage of large language models and huge deep learning models in the robotics domain, is to connect the knowledge that's embedded inside the large language models, LLMs, with some sort of sensory input of the robot and actuators of the robot. So consider ChatGPT, for example. It has a knowledge of the world, right? It has actually a project knowledge of the world in the sense that there is a projection of the world to the text modality, and the large language model sees all the world to the natural language. So this is like the example that Ilya Sutskever gives. And what's surprising is that with that projection, you can solve many different tasks. So it turned out, for example, machine translation can be done without knowing what blue means. So even though large language models don't know what blue means, what blue corresponds to, or what a border corresponds to, can translate a sentence from any language to any language, basically, because it has seen a lot of projections from different directions and kind of developed an idea of what the world looks like. But even then, there are some reasoning problems that you can get with large language models such as ChatGPT. So you can ask some arithmetic questions, reasoning questions, or like intelligence testing questions, and you can get some incorrect answers. It's because, as I said, the model doesn't actually have an understanding of the world. And one idea one recent idea in robotics is that maybe we can connect the LLM with the real world by just giving some labeled data, and then we would be good to go. So this is one approach that I might say might actually work. Here the idea is that we leverage the reasoning part of the problem to large language models. But what we can actually do is this reasoning, the problem of reasoning actually has been studied in AI for like 50 years or something. So here you see the Cake robot. This experiment is from 1971, and it has some sensors on it, and it senses the environment through these sensors. And there are some predefined classifiers that gives you some namings for different sensor input. For example, when you see a box model, when the model sees a box through its camera, it can parse that it's a box and so on. And on the right, you see a domain-specific language, which is called Problem Domain Definition Language, in short PDDL, that defines some high-level actions and how these high-level actions change the environment configuration. For example, if we take a look at the action move, it takes two parameters. Here, the entities that starts with the question mark are variables. So here it takes two variables, two parameters, and there's some precondition to these parameters. So if these parameters satisfy that the from variable is a room, to variable is a room, so like these from and to variables needs to be room. And if at Robbie, in our case, in this example, let's say the name of the robot is at Robbie. If at Robbie is indeed in the from room, from variable, then this precondition is satisfied. And when we move from location to a to location, what happens is that now at Robbie to predicate turns on, which is like this predicate becomes active, and at Robbie from becomes inactive. So this actually shows you a very basic reasoning step where we say that if a robot moves from a room to another one, these high-level predicates change. So this is a very nice idea where you basically say that there are some high-level predicates, and you can think of them as symbolic representations that can take two values, like being active or inactive. And then you can write these action schemas for that represents the skills of the agent. For example, if the agent can pick an object, you write an pick action. If the agent can drop an object, you can write a drop action, and so on. When you define such a domain, and if your robot can indeed find truth values to these predicates, then reasoning part is actually very easy. You can do tree search, you can use off-the-shelf AI planners to reach any goal soundly and in a very fast fashion. But the problem is how to define these symbols. So like in this shaky example, there were only a handful of symbols, and these are predefined. But in the real world, how would you know that which symbols you should define? Like for example, if you want a robot that cleans our living room, what should the symbols be? Like, should it be just symbols for objects? Should it be symbols for the locations of the room and so on? And we don't know how these symbols should be defined as well. Like, should we train classifiers on them for them? So these are the main drawbacks of this approach. So these are the things that limits the symbolic AI paradigm. But if we take one step back, this is the main problem that we want to solve, right? There is an agent, there's an environment that's the real world, and the agent senses the environment through its percepts, through using its sensors, like cameras and so on. And it does some computation inside, we don't know what, and then through its actuators, it executes an action in the environment. And this question mark, this black box, is the thing we want to solve. And deep learning just throws a very large model on it and let it says that let it be learned, let all be learned in this black box. But this is, by the way, from the book of Stuart Russell and Peter Norvig, Artificial Intelligence, a Modern Approach. It's a very good book. I can suggest that you can take a look. And in this book, it's like starts from this one and shows that, okay, what a simple reflex agent can do. Like a simple model of an agent can be something like this. It senses the environment. So this basically gives you the answer of what the world is like now, and conditioned on that world configuration, you can choose what action I should do now. So you can think of deep Q networks or some basic RL agents are doing something like this. You can embed more information into your agent. Say you sense the environment, but you construct a belief state for the current configuration of the environment. Maybe your sensors are noisy and you don't trust whether that thing you see is correct or not. So you build a belief through time about your state that you are currently in. And you might know how the world evolves. For example, given this state, you might have a knowledge of how the world will evolve given that state. And you can embed how your actions modify the world around you. And then based on that knowledge, you can take an action. That'll be a much better agent because you now have an understanding of the world. You can embed goals into your model, into your agent. Like the agent can simulate how its actions change the world, and then you can check whether the action that you take satisfies your goals or not. You can change the goal from an true or false entity to a utility, like a metric-based system where you now sort your states based on some preference and take actions that increase your utility. So this introduces some structure into the agent instead of just throwing a very large neural network. And what I want to say in this talk is that I think we should throw as much as knowledge as we can, as much knowledge as we know actually about the world, because otherwise we cannot generalize to out of the distribution novel scenarios that is going to happen in the real world, because real world is like you cannot get enough data to model real world. And for example, this introduction of structure into deep models is done in the AlphaGo, where the AlphaGo beats the world champion Lee Sedol in 5 games, in a 5-game competition where it's won 4-1. And the structure that AlphaGo had was in addition to a deep neural network that recognizes that takes the Go board configuration as input. Now it can simulate the game using Monte Carlo tree search method to get an estimate on the value of that state. And what this showed is that using some search techniques, you can get a better estimate of the state, and now you have a better estimate of the state. Now you can take better action. So this shows that, oh, we can introduce some simulation of the model into the agent, and that will increase our performance. And that makes sense, right? Because if you have a knowledge of the world, it actually makes sense to simulate it and like get an estimate on the value of those states. And this AlphaGo work takes the, of course, as a knowledge of the Go game, right? Like it doesn't need to recognize the board through physical pieces. So the system already knows which piece corresponds to which piece, the whole board configuration. It has the knowledge of that there are 19 by 19 different locations that a piece can be. But this is not the case in the real world as well, right? If we go one step back, if you consider a robot that needs to play chess, Go, or any board game, it first needs to recognize the positions of pieces, what each piece means, like it needs to differentiate between a knight piece, between a bishop and pawn. It needs to recognize their positions, and it needs to understand the game by observing how a chess is played through multiple episodes. And there are here two problems, actually. Like one is percepting the current board configuration, and the other is playing good chess, and that's the reasoning part. What I will now what I defend is that I think you can split this problem into two, at least two, where in the first part you percept your environment configuration, and then you can do the reasoning by using off-the-shelf AI planners to get a decent chess performance. Maybe not the world champion level, but you can get a very decent performance with basic tree search. So here, for a general purpose robot, the problem then is reduced to recognizing the environment based on the specifications of the task, and then actuating in the environment for that specific task. And you can actually say that there are actually much more divisions in this problem. Like you can divide it into perception, reasoning, navigation, and motion. For example, here there's a robot collecting items in the room into a bin. Now there's another problem, which is navigating through the room, right? And that you can, what I'm saying is that we can consider this problem as a separate, isolated problem and develop solutions for that specific problem. And there are actually very good solutions for navigation problem of the robot. Consider your robot vacuum cleaners. You can say, oh, go to this room, and it navigates to that location fairly easily. There is the problem of motion planning, where you need to figure out how your robot arm should position in order to execute a skill successfully. Let's say you want to open a door. You don't want to stand just behind the door because your body, your embodiment, prevents the door to be opened. And you need to figure out where you should be in order to successfully open that door. But that's another problem than the problem of, let's say you want to go out and you generate a very high level plan. Okay, I need to stand up. I need to go to the door. I need to open the door. I need to go downstairs, and so on. So that's like a high level plan, and details of that plan are actually a separate problem. How I walk to that location, how I turn that doorknob to open the door are actually different problems. Treating that whole thing as a one problem, that is the current paradigm. That is the current paradigm with deep learning. That is the current paradigm with LLM based reasoning. Is I think would be insufficient in the long term. So I believe I give some enough motivation about why we wanna split this problem into different parts. So this is basically saying that any structure in the real world, if there exists any structure in the world, we should exploit them. So by structure, I mean if we have an understanding of the navigation pipeline, which basically what simultaneous localization and mapping does, we can use that. We have motion planners to like figure out what the robot arm, where the robot arm should be to execute collision-free motions, then we should use that. If we know that the environment consists of objects, then we can build our representations we can build our algorithms based on the objectness of the real environment. And this is the video that motivated me to make a PhD in the field of robotics. So before that, I was doing machine learning. Before that, I was doing some research on generative adversarial networks. That's kind of like an unsupervised method to learn representations. But after I see this video, there was a spark on my head that said, "Oh, any representations that we develop should be based on the current skill set of the agent." So here you see the baby exploring its environment by manipulating objects, playing with them freely. It develops an understanding of the world, the environment, through playing with its environment. So any representation actually helps the agent to in the future how it can manipulate its environment more efficiently. So I want to give another example of why we would want to develop representations that are based on our current action set. Consider a robot that can fly and that cannot fly. So consider these two robots. In one, you might need to, for a flying robot, maybe you may want to understand whether you can pass through a gap, whether you can pass through a very narrow street or like a very narrow window, whereas you don't care about that representation if you are a vacuum cleaner robot that are navigating it on the floor of the room, because the robot that navigates on the floor doesn't need to understand anything about the windows, doesn't need to understand anything about the narrow gaps that are on parts that cannot be reached by that robot. And if we have two arms, if we can manipulate objects with two arms, we should develop representations that considers the current skill set, current embodiment of the agent. And the second thing is that here the agent, like in our case the baby, plays with entities, and these entities are isolated from each other. Like they are separate entities, and babies actually learn that these objects are separate things. And this is another structure in the real world that we can use to build much more efficient representations and algorithms. And through my PhD, we research on some systems that has these three requirements in it on the high level. Firstly, we should learn object level symbols to represent the environment, because tasks we care about consists of objects, multiple objects in the real world. And the learned as the second requirement, the representations we learn should encode the preconditions and effects of actions of the robot. So what do I mean by this? I mean, in order to, so the representations you ever need is whether you can execute an action given that current world configuration, and when you execute that action, what would happen? because if you can model these two things, then you can simulate the world around you by chaining, oh, if I grasp this cup, then the cup would be in my hand. And if I move together with the cup, then the cup will move together with me. So these are the things that you want to model. And anything that are apart from the encoding, that are not in the actions that cannot be changed by your actions are irrelevant. And as the third thing, this system should support differentiation because you want to utilize the recent techniques from computer vision, from other subdomains of machine learning, and you want them to be modular, you want them to be positioned as a plug and play kind of system. So if you get a new state-of-the-art object recognition model, you want to be quickly able to remove the previous object detector and plug in the new one. And currently, this can only done through the support of differentiation, where all parameters can be trained through backpropagation by finding out how that parameter affects the final performance. And to satisfy these requirements, we proposed DeepSim, where we learn object symbols that encode effects of actions with deep neural nets. And with learned symbols, and by symbols now, I mean, remember the predicates that we had in the symbolic AI system. So these symbols are basically truth values that are either true or not. So it can take two discrete values. And these are you can think of them as that take an input, that's a continuously valued input, and outputs 0 or 1. So it's like a mapping from a continuous world to a discrete world, to a Boolean values. And if we can learn object symbols that encode effects of actions, then what we can do is we can use them those learned symbols for planning purposes. And this was the general high-level view of the architecture, where we have an encoder and a decoder, and encoder gives us a latent representation. This latent representation is binarized, and so this is basically if a number is higher than 0, then you say that actually corresponds to 1. If it's lower than 0, you say, okay, that corresponds to 0. So in a way, from continuous values, you can get symbolic representations. Here, the problem, though, is that this operation is not differentiable, and you need to use some sort of approximation techniques to get the gradient through this binarized activation. And the decoder, given this symbolic representation of the object together with the action, the decoder predicts what happened to the environment. So it predicts the effect that this action observed, that this action exhibited. Now I want to give an example of what kind of representations learned and what is the experiment setup. So here we see a manipulator arm that's executing some simple actions on objects by pushing them through different directions. And there are different kinds of objects here, like cylinders, cubes, boxes, and so on. And after we train this network with the interaction data we collected from here, where we give that image of the object as input to the encoder and try to predict what happens to the object after we execute the action. And here the effect is represented as the Cartesian displacement of the object. These are the representations these are how different objects activate different symbols after the training procedure. So here, for example, these on the second row, this set of images, as you see, these are kind of like cylinders, activate the symbols 0 and 1. And these box-like things activate the symbol 1, 0. And you see, just by predicting what happens to the object, what you get is you get symbols that actually is bound to different objects. And that is nice, right? Because now we have a way to understand the categories of these different objects. In the first row, though, you see different objects are placed into the same category. So it's like upright cylinder and cube are placed, actually activate the same symbol, which is 0, 0. This is actually, this makes sense in this context because the actions that the robot executes to these different objects shows the same effect regardless of these two different types of objects. So even if you push a cylinder from different directions or a box from different directions, you get the same effect, at least if you push them from specific directions. So what I want to get is that with this current skill set of the robot, these two objects are inseparable. So for the purposes of the robot, these two objects are the same. And this is the property that we want from our system. And this is another set of demonstration that we learn. This is another set of interaction data with the real world, where the robot takes one object on top of the other. And here, by utilizing previously learned symbols for these objects, what the network discovers is the relative sizes of these objects. And now I'll skip some details, but please feel free to ask any questions and correspond with me after the talk. After we get these, after we learn these high-level symbols for this environment, what we can do is we can transform that environment into a discrete rule, which is like if such and such symbol are active, the effect I get is something like this. So we can translate this continuously represented knowledge into something discrete, something that can be translated into a rule, and then use them for the purposes of planning. Here, after adding some manual predicates, some manual rules, given a system like this, where the robot recognizes the scene from a top-down camera and asks to construct a tower with 4 objects, and we want that tower to, and we specify some height to that tower. Let's say we specify that tower to be a height of 1. Then the robot can, the system can generate the correct sequence of action that satisfies such goal. Here you see the problem definition that is generated automatically through these encoders that are learned. And these bolt typed symbols are actually the symbols that are learned through the interaction phase. Now, what's non-trivial, what is learned in this situation is, let me show you another example. Now, we want to construct a tower with height of 4 using 4 objects. So what is non-trivial about this thing is that we recognize the scene, we developed categories, we learned symbolic representations for these objects, and we learned paired relations between objects. And this is done only through the prediction of the effect for different actions. And what we show here is that we can use such representations for the purposes of planning. So in a sense, here we are kind of doing a reasoning. So for example, the model can reason about, oh, I need to put that box first because otherwise the other box, the smaller box would drop, it would be inserted in the larger box, and so on. So instead of reasoning through LLMs or some other deep models, what we can do is if we build the necessary symbolic predicates for these entities in the environment, we can actually do this reasoning fairly easily. That's like the gist of my method. And let me skip this here. There are now different kinds of objects, and we ask the robot to construct a tower of height 5 using 5 objects. Now, because the robot has an understanding of its environment, now it correctly places the sphere on the top because it knows that it learned that if we put an object on top of a sphere, that object would tumble, and we cannot construct a stable tower. So this is like a very prototypical proof of concept kind of experiment that shows shows an evidence for our method. And since I don't have enough time, I'll skip some things. I'll show another example where using some modified version of this method, given an initial configuration like this, where there are some cubes and long blocks, and we want to achieve a goal configuration like this, where the cyan block is on top of the green one, and the yellow block is on top of the cyan one. And with the method we developed, we can translate the continuously represented environment into a symbolic form, and we can ask what sequence of actions we need to take to achieve that goal. And here you see the system generates the correct sequence of action to achieve that high-level goal. Here you see the model has an understanding of the environment that if we take this long block, the block on top of it will move together with the long block. So this is done just by trying to learn a representation where we try to encode the preconditions and effects of actions. Here's another example from this initial configuration. We want to reach to this goal configuration. You see the model has an understanding of this sliding effect, and it can produce the correct sequence of actions to achieve that, to reach to this goal state. So to conclude, we should indeed use deep networks. So there's definitely an advantage of using deepness because they learn distributed representations, and it has been shown that distributed representations give us representational advantage over local representations. But the way we learn, the way we position these deep networks can might differ, and actually should differ for robotics. And if you want to build a high-level system that works in the real world, we should position them very carefully, and we should utilize the structure in the world. And here we only try to predict the effects of actions for each different object, and let the reasoning part handled by the AI planners. Because once we learn the correct symbols for the objects, we can make tree search and get a fairly good performance for any kind of task. The advantage is that this model that we proposed can be trained in an end-to-end fashion to minimize the effect prediction, which is like in line with the current paradigm of deep learning. So we can throw the data in and learn representations out. But these representations are not directly to predict the action. Instead, these representations are symbolic representations for different objects. And any differentiable module that is developed, that is new, can be integrated to this approach. For example, you can employ a new convolutional net, a new computer vision module on top of this system to get a better performance at a specific domain. And there are some, of course, limitations to this work, which is you need to define your actions. So we learn all the representations we learn here assumes that we have an access to high-level actions, so like pushing objects from different directions, maybe stacking objects on top of each other. But when you think about the real world, you can actually code. I mean, it's fairly reasonable to say that you can code these skills. For example, if you want a household robot, the general skills would be picking objects, placing them, maybe opening doorknobs, opening cupboards or drawers, and so on. And that can be actually limited down to a fairly small set of actions. We assume that the world is the second important assumption is that we assume that the world consists of objects, and we develop our representations from an object-centric perspective. And this assumes that you have an access to an object segmentation module, and not only that, but you know that the world is only and only composed of objects. So this might give some incomplete behaviors in maybe some domains, for example, where you want to extract some information, or you can manipulate some sub-object feature. And the third thing is that we need to have a good effect representation. In our case, we use Cartesian displacement of objects as our learning signal, but assuming that the effect is a Cartesian displacement, you lose some granularity, you lose some of the things you can model. And that's all of my talk actually. I hope it was not very deep or like very wide. Thank you.
Hocam
Teşekkürler.
sunduğunuz için çok teşekkür ederiz. Dilinize sağlık.
Rica ederim.
Ee,
Umarım
izninizle
istenilen
buyurun.
anlaşılırlık düzeyinde olmuştur yani. Biraz daha motivasyon vermeye çalıştım aslında. Metodumun çok detaylarından bahsetmek yerine hani daha çok neden bu problem üzerinde çalıştığımız üzerine biraz konuşmak istedim.
Teşekkür ederiz hocam. Yani bence gayet güzeldi. Tekrardan emeğinize ve dilinize sağlık. E, e, Müsaadeniz
Ben
olursa
teşekkür ederim.
çete bir soru gelmiş.
Tabii,
Önce onu sorayım. Sonra ben de birkaç soru hazırlamıştım. Onları
tabii.
soracağım. Deep Symbol Generation ve Rule Learning'in gelecekteki potansiyelini nerede görüyorsunuz şeklinde bir soru gelmiş. Yani bu kavramlar gelecekte bizim için ne düzeyde önemli olacak veya ne alanlarda e, önemli olacak şeklinde bir soru diye yorumluyorum esasen.
Evet, yani benim öngördüğüm durumda e, bu derin öğrenme yapılarıyla yani deep neural netlerle sadece sensör information alıp action tahmin etmeye çalıştığımız modeller bir noktada tıkanması gerekiyor. Yani bu kadar veriye ne yazık ki erişimimiz olmayacak. Yani ChatGPT'nin çalışmasının sebebini aslında tüm internet boyutunda bir veriyle eğitilip e, aslında sadece doğal dili modellemesi. Ama gerçek dünyada yapacağımız her şey için aslında bir şekilde problemin daha isolate edilip farklı kısımlarının farklı şekilde çözülmesi gerekiyor. Burada da yani objelere dair sembollerin öğrenilmesi ve o objelere dair semboller üzerinden manipülasyonlar yapılarak reasoning yani muhakeme yapılması gerekiyor diye düşünüyorum. Bunun yani daha doğrusu bunun aslında uzun vadede yani uzun vadede bu şekilde bir yaklaşımın bizi daha e, daha intelligent behavior'a götüreceğine inanıyorum.
Teşekkür ederiz hocam cevabınız için. Ee, Şey sormuş olayım hocam, hani potansiyelinden bahsetmişken şu an biz bu potansiyele ne kadar yakınız? Yani e, deep learning çok gelişti, yani bundan belki de 5-6 yıl öncesine kadar çok basit düzeydeydi ama bir anda makine öğrenmesi, yapay zeka, bu konular çok hızlı yükseldi. E,
Evet.
Benzer bir durum bu alanda da var mı? Yani şu an biz bu bahsettiğimiz potansiyelin hangi seviyesine gelmiş olduk?
Benim yaptığım işler aslında prototipik örnekler diyebiliriz. Yani çok basit deney düzeneklerinde aslında çalışmalarımı yaptım ve gösterdiğim şeyler de çok basit muhakeme örnekleriydi. Yani çok basit reasoning e, görevlerinde hani çalışıyordu. Ama aslında bu işin güzel yanı kurduğumuz sistemi diğer sistemlerle birleşebilir şekilde yapmaya çalıştığımız için aslında bu modülün yani differentiable olmasını istememin sebebi de buydu. E, Aslında çok yeni çıkmış diğer deep learning modellerini direkt entegre edip bu sistemi kullanarak çok daha iyi semboller, çok daha fazla büyük verilerle yani çok daha genel semboller öğrenebiliriz ve bunları yine reasoning tasklerinde kullanabiliriz. E, Yani aslında olay yani bu problemi e, frame etme şeklimiz şu an şey gibi. Biz bu sistemi nasıl yapılandırmalıyız ki bu bize high level reasoning e, olanağı sunabilsin. Ve aslında bunu doğru yani e, deep learning'deki aslında her gelişmeyi kullanabiliyoruz bu şekilde. Çünkü zaten kullandığımız modeller deep learning modelleri oluyor. Sadece aslında soruyu cevaplama şeklimizi değiştirmeyi öneriyoruz. Hani,
Anladım. Teşekkür ederim hocam cevabınız için.
yani,
Ee, Benim bir diğer sorum hocam, e, bu alanda yapılan çalışmalar endüstriyel manada, yani iş dünyasında ne gibi bir etkilere sahip olabilir? Gelecekteki iş modellerini nasıl etkileyebilir? Bunu sormak istiyorum esasen.
evet.
Bilmiyorum ne kadar alakalı bir soru sordum ama.
Yo aslında alakalı yani mesela bir yani endüstrideki aslında tüm işlerde eğer siz mesela bir model geliştiriyorsunuz, o modeli gerçek dünyada çalıştırmak istediğinizde size ilk sorulan hani bu model gerçekten çalışıyor mu? Hani bunun çalıştığına karşı tarafı ikna etmeniz gerekiyor ve e, yani şu andaki kullanılan yapay öğrenme, derin öğrenme gibi metotları karşı tarafa bunların kullanılabilirliğini kanıtlamak istediğinizde yaptığınız şey işte bir performans metriğinde işte bakın bu test verisinde bu kadar başarılı oluyor. Hani bizim yaklaşık öngörümüzde şu kadar başarılı olacağı gibi şeyler. Aslında burada sembolik gösterimler öğrenip bunların üzerine kurallar inşa etmenin getirdiği bir diğer avantaj bu modellerin direkt şeffaf olması. Yani sistemin çalışma mekaniklerini siz karşı tarafa anlatabiliyorsunuz. Bakın işte burada böyle bir sembol öğrenilmiş. Bu sembol şuna karşılık geliyor ve aslında sistemin öğrendiği şey işte şu semboller aktif olduğunda ve bu sembollerin ne olduğunu biliyorsunuz. Bu sembollere dair grounding yani bunlara tekabül eden gösterimlerinizi de biliyorsunuz. Buradan şey diyebiliyorsunuz yani işte şu durumlarda model bu şekilde bir davranış gösterecek ve bunu direkt kesin olarak biliyorsunuz. Yani burada e, modelin tüm e, behavior'ını aslında e, daha şeffaf ve bütün bir şekilde tanımlayabiliyorsunuz. Ama bunu e, yani direkt derin öğrenme modelleriyle karşılaştıracak olursak e, farklı girdilerde nasıl çıktılar vereceğini her zaman bilemeyebiliyorsunuz. Çünkü hani modellemeniz gereken uzay tüm sürekli yani tüm continuous valued uzayda gezemeyeceğiniz için diyelim bir image classification modeli hani orada her farklı image için nasıl bir sonuç alacağınızı bilemediğiniz için hani e, buna dair cevap veremezken daha bu sembolik gösterimlerle aslında modelin nasıl çalıştığını biliyorsunuz ve bence endüstrideki en endüstrideki en kullanılabilir e, yani bunun endüstriye getirdiği en önemli avantaj bence bu şeffaflık birincisi. İkincisi aslında probleminizi e, uh, current state, the action we applied and the effect we observe şeklinde modelleyebileceğiniz bir sürü alan var. Yani siz bunu şey de diyebilirsiniz. İşte benim e, aksiyonum yaptığım satış pazarlama aksiyonu. Ben bu işte şu satış pazarlama aksiyonunu yaptığımda benim state'im şu şekilde değişti ve bunları yani bu genel bir framework aslında hani herhangi bir domaine uygulanabilecek çok daha genel bir framework ve e, endüstrideki çoğu problem de hani current state, the action we applied and the effect we observed şeklinde frame edilebilir diye düşünüyorum. E, ve yani bu şekilde daha şeffaf ve bütün modeller üretilebilir. Derin öğrenmeyle kıyaslandırdığımızda. Zaten ki derin öğrenme modellerinden çok işte karar ağaçları, decision trees, XGBoost gibi modellerin kullanılmasının da ana sebebi aslında karşı tarafın yani müşterinin şeffaf çözümler istemesi. Yani bu çözümlerin nasıl çalıştığına dair bir bilgilerinin bilgi sahibi olmak istemeleri.
Anladım hocam. Çok teşekkür ederim cevabınız için.
Yani,
Ee, Bir diğer sorum, bu alanda çalışanların bireysel, yani sizin de merak ediyorum, genel olarak da merak ediyorum. Karşılaştığınız en büyük zorluklar nelerdi? Teknik olarak olabilir, diğer açılardan olabilir.
e, ya özellikle robotik alanında hani belki yapay zeka alanındaki teknik zorluk pek yok denilebilir. Yani her şeyi zaten kağıt kalem üzerinde bile çalışabilirsiniz. Hani gerekli şeyi teoriyi ürettikten sonra. Ama işin robotik kısmında aslında çok fazla teknik detay var. Yani ben mesela burada şey dedim ben objeleri mesela örneğin şurayı açayım videoyu. Burada hani objeleri tek tek tanıyıp segment ediyorum dedim. İşte tek tek objeleri tutmayı yani birini tutup diğerinin üstüne koymayı biliyorum dedim. Bunları hani birazcık hand wavy yani şeyden biraz daha böyle ya bunlar yapılır bir şekilde gibi söylüyorum ama aslında bunlar çok ya pratikte yapması zaman alıcı ve yani uğraştırıcı şeyler. Yani burada objeyi işte tanıdık, hadi tanıdık diyelim tam orta pozisyon neresi, tam ne şekilde tutmam gerekiyor ki düzgün şekilde kalmasın, elinden düşmesin. Ve burada sadece statik bir environment'ta deney yaptım. Yani bunun içinde navigation yok ama diyelim gerçek dünyada elinizde bir spot, işte Boston Dynamics'in spot robotu var. Bir odadan diğer odaya giderken, işte kapıyı açarken karşılaşacağınız hani gerçek durumdaki e, zorluklar çok daha fazla. Yani bunların e, modellemesi ya bunların modellemesinin zorluğunun dışında bunlar üzerinde deney yapmak da zor. Çünkü gerçek dünyada deney yapma hızınız çok yavaş. Simülasyon kullanırsanız da e, simülasyon bu gerçek dünyadaki e, keskinliği bazen yansıtamayabiliyor. Veya simülasyonda yeterli miktarda çeşitli obje bulamayabiliyorsunuz. Mesela diyelim yastık gibi bir objeyi modellemek istiyorsunuz. Tabii ki çeşitli işte soft objeler modelleniyor simülasyonda da ama Hani tam anlamda bir tam anlamda bir gerçek dünya gösterimi gibi olmuyor. Ve bu yüzden aslında simülasyonda eğitilen modeller ile hani gerçek dünyada deploy edilen modeller arasında bir hani sim to real gap dedikleri bir gap oluyor. Bu gap'i işte yani bu gap'i daraltmak için işte çeşitli teknikler üretmeye çalışan bir domain bile var yani. E, Bu en büyük problem yani hani zaten belki de robotiğin diğer alanlara göre bu kadar hızlı gelişmemesinin de sebebi veriyi bu kadar kolay toplayamamamız, yani veriye ulaşımımızın bu kadar çok olmaması. Hani internet scale data ile işte internet scale kadar olacak bir robotik datasını toplamak çok zor. E, Yani bu işte en fazla belki otonomous driving'de olmuş olabilir, yani toplanmış olabilir. Herkes sürüyor arabasını, arabadaki recordingler kaydediyor falan ama e, ya onun dışında bunu gerçek dünyada toplamaya çalışan şirketler var bu arada. Yani gerçekten humanoid bir robotu oynatıp işte bir yıl boyunca çeşitli household environment'larda oynatıp veri toplayıp gerçekten tamam bunun üstüne kocaman bir network fırlatıp çözeriz destekleyen e, şirketler ve yöntemler var. Ama yani dediğim gibi şeyler e, dünya konfigürasyonları e, çok çok farklı olabileceği için hani bunu bu kadar büyük veri toplamak uzun vadede ne kadar sürdürülebilir tartışılır. Yani zorluklardan biri gerçek dünyayla uğraşılması diyebilirim robotikte. Ve birden fazla sistemi entegre etmeye çalışmamız. Hani bunun içinde navigation planner var, işte motion planner var, e, object recognition kısımları var, actuation kısımları var. Bunlar daha zorluk getiriyor yani belki diğer AI'nin diğer domainlerine kıyasla.
Çok teşekkür ederim hocam bu detaylı cevabınız
Tabii.
için. Chat'i hemen bir kontrol edeyim hocam başka soru var mı diye. Chat'ten yok. O zaman ben son olarak şeyi sormuş olayım hocam. Bu alanda çalışmak isteyen gönüllülerimize, arkadaşlarımıza ne gibi tavsiyeler de bulunabilirsiniz? Ne gibi kaynaklara bakabilirler? E,
E,
Onunla alakalı.
Öncelikle şeyi söyleyebilirim. Şimdi ben de kendi slaytlarımda işte Symbolic AI deyince çok eski bir robotu falan gösterdim. Yani bu şu an şey algılanıyor. Hani AI denince işte yapay zeka denince akla tek gelen yöntemler işte yapay öğrenme, e, machine learning alanı geliyor akla. Ve yani bu da şu an hani işte derin sinir ağlarından oluşuyor. Aslında sadece bundan ibaret değil yani bu yani tek çözüm de bundan ibaret değil. Hani daha farklı çözüm yöntemleri var ve zaten insanlar da sadece neural netlerle çözülmeyeceğine karar verip biraz daha neural netlerin içerisine de structure entegre etmeye çalışabiliyorlar. Benim hani şey yapabileceğim tam tavsiye niteliğinde değil ama biraz daha propaganda niteliğinde aslında bu sistemlere structure entegre etmek kötü bir şey değil. Hani aksine bence bu iyi bir şey ve gerekli bir şey. Hani yani bu düşünceyle biraz daha problemlere bakıp hani çalışma, araştırma alanlarını belki buna göre belirleyebilirler. E, Onun dışında kaynak olarak Stuart Russell ve Peter Norvig'in bu Artificial Intelligence a Modern Approach çok güzel bir kitap. Hani bu alanda böyle genel bir özet primer niteliğinde ve hani güzel bir referans kitabı olabilecek bir nitelikte. Yani bu kitap aslında direkt alınıp okunabilecek netlikte bence. E, Onun dışında yani çalışma alanlarını belki daha büyük problemler, büyük hedefler olarak belirleyebilirler. Ben doktorama başladığımda aslında şey olarak yani hiç şaka yapmadan şey diye gitmiştim. Tamam ben bu tüm AI problemini çözeceğim işte. Bunun tabii ki tek başıma yapılamayacak bir hedef olduğunu biliyorum. Hani bu şey gibi yani tek başıma Ay'a çıkacağım gibi bir absürtlük seviyesinde yani, ama yine de o büyük hedefte, yani o hedefe yönelik çözümler üretmeye yönelmek gerekiyor bence. Yani bunu yapan kişi sayısı az şu an yani. Direkt tamam, ben işte şu büyük problemle uğraşacağım, hani sadece o problem önemli ve o problem üzerinde çalıştığım diyen kişi sayısının bence daha artması gerekiyor. Yani şu anda yani machine learning'in getirdiği avantajlar ile e, biraz daha e, yani akademik araştırma şeye yönelmiş durumda. E, Bazı küçük narrow problemler var ve o narrow problem üzerinde çok iyi performans elde edeceğim. Yani o narrow problem üzerine çalışıyorum. E, Ama hani bunun hani daha e, büyük resimde böyle tabii ki o problemi çözmede yardımcı oluyor, ama biraz daha büyük problemi de çözmeye çalışacak insanlara ihtiyacımız var bence ve burada çalışan kişi sayısı az bence yani. Biraz daha belki bu büyük problemlerde e, çalışmayı, yani bu daha böyle büyük geniş problemlerde çalışmayı hedef koymayı önerebilirim. E, Sadece AI alanında değil, başka alanlarda da aslında bu şekilde.
Çok teşekkür ederiz hocam tekrardan.
Yani,
Yani özellikle sabah bu saatinde her ne kadar Türkiye'de şu an 17 olsa da saat Amerika'da saat 12
estağfurullah.
sanırım. Ee,
Evet,
Bize katkı sunduğunuz için çok teşekkür ederiz. CS
rica
Talk
ederim.
serimizin buyurun.
Umarım yani biraz farklı bir böyle konuda güzel bir motivasyon vermişimdir diye umuyorum. Ve yani e, daha sonrasında da hani herhangi bir soru veya bu konu hakkında bilgi almak isterseniz, hani web sayfamda e-mail adresim de mevcut. E, Herhangi bir zamanda hani herkes e-mail atabilir.
Çok teşekkür ederiz hocam. Eğer eklemek istediğiniz herhangi bir nokta yoksa CS Talk serimizin 13. bölümünü sonlandırabiliriz. E, Tekrardan çok teşekkür ederiz.
Rica ederim.
E, görüşmek üzere hocam.
Görüşmek üzere. Tekrar